Let's do number 4 here. So I already drew a picture that we have two wires that carry a current in the same direction. So that's this wire here and that one over here. Midway between them, we have a third wire carrying a current in the opposite direction, and it's half of the current as the other two. So that's how we want to visualize. And the first thing is, in which direction are the net forces on the outer wires? So the first thing is we need to visualize, well, why is there a force on an outer wire? So let's pick this outer wire over here. Why is there a force on this one? Well, there's going to be a force from this one, so I'll call this wire 1, wire 2, and wire 3. So there's a force from number 2 acting on number 1. And when they're in opposite directions, the force is going to be repulsive. So this is going to be F21. And we can find an idea for the magnitude of the force per length. We don't know how long these wires are, but we have an expression for the force on a wire per length of that wire is equal to the permeability of free space times the product of the two currents, so I1 and I2, divided by 2 pi d, where d is the distance between the wires. So we can get kind of an amount for this force that we can plug in that we have a current I for the first one, but for the other wire we have half of the currents. So those are the two currents, and I'm not going to worry about a constant. I'm just trying to find out how big is this force. And then the distance, I'll call this distance, I'll call it d. So the distance is d. So this gives you an idea of the force between these two wires, that there's a factor of 1/2 on top. There's no extra factor on the bottom. You still have the mu and the 2 pi here. I'm just not writing them because they're going to apply to all the forces. And now I'm going to look at the force between 1 and 3. So when the currents are in the same direction, the wires are going to attract each other. So what is the amount of this force? Well, this time, if I plug in what I know, the two currents are both the same. You don't have one that has a factor of 1/2. However, for that distance, it's twice as far. So the distance between 1 and 3 is 2d. So for the force between 1 and 2, we had a factor of 1/2 on the top. Forces between 1 and 3, we have a factor of 2 on the bottom. That's equivalent. This is still a factor of 1/2 here, because you're dividing by 2. So it turns out that because here you have half the current, but you're also closer, while here you have more current, but you're further away, the two forces are exactly the same, but they're in opposite directions. So the net force on this wire is going to be 0. You could do the same thing for the force on wire 3, and you'll get the same answer. Number 5. A proton is released such that its initial velocity is from right to left across this page, so it's going this way. The proton's path, however, is deflected in a direction toward the bottom edge of the page due to the presence of a uniform field. So there's going to be a force downward that deflects the path of this particle. So what's the direction of the field? So you need to use the right hand rule. So let's see if I can draw it for you, since you can't see my hand. But this is the third right hand rule that we learned, where we point our fingers in the direction of V. So first your hand is going to point this way, your fingers to the left. And then that's V here. And then you're going to fold them towards the direction of B. Now right now you could have your hand like this. You could also have your hand with your fingers facing to the left. You could just have your hand like this. Or these are all your 4 fingers here. Right, so you don't really know how to orient your fingers. You just know that your fingers are to the left. But now you know that you're going to have to fold your fingers in the direction of the field so that the thumb points down. Right, so if you have your hand like this, where the palm of your hand is facing the paper, it's parallel to the paper, then you can actually fold your fingers into the page. So that would look kind of like this. It's kind of hard to draw, but your fingers are folded into the page. There's a 90-degree angle here. So this is B into the page, so that you could have an X here for the B. You still had your V was going this way. And now your thumb that was here is now pointing down if you're doing this. Oh, whoops. So there's your thumb going down. And that's exactly what we want. So that's how we know that B must be going into the page to get the thumb down. Now if originally you had your hand perpendicular to the page, well, if you folded your fingers down, so now it's going to look like this. Your fingers are pointed down here. That doesn't look very good here. So your fingers are pointed down. Well, in this case, your thumb would be coming here out of the page. Right? This would be a 90-degree angle. This thumb would be coming out of the page. That would be a dot. And that wouldn't be down. So if the thumb were coming out of the page, that's a dot. Then that just means that you haven't oriented your hand in the correct way so that you can have your thumb pointing straight down like we want for the 4s. To make a long story short, the field must be into the page. So we can put a big X next to this because this doesn't work. Let's do one more here. So there's a current I flowing in a clockwise direction in a square loop. It's in the plane of the paper. That means parallel to the paper. Paper is what this is printed on here. Magnetic field is towards the right. Each side of the loop has a length L. Then what's the net torque acting on the loop? So the equation for torque is mu b sine theta, where mu is the magnetic moment, and the magnetic moment is defined as NIA. And the direction of the magnetic moment is going to be in a direction perpendicular to that area. So the area is in the plane of the paper. So in this case, the magnetic moment would actually point into the page. And I used the right hand rule what I did is I folded my fingers in the direction of the current and my thumb pointed towards the page. So that's how I knew that was the magnetic moment. And this theta here is defined as the angle between mu and b. So we have mu going into the page, this way, into the page. There's a 90-degree angle here. This is mu. So first of all, before trying to use the equation, you need to know, is there going to be a torque on this loop in the first place? And there will be, because the magnetic moment is perpendicular to the field. It's going into the page while the field is going to the right. Now, if the loop had been drawn like this, where the loop was perpendicular to the page, right, and the field is going this way, and let's say the current is going this way on this loop, well, that means that the magnetic moment and the field would both be going this way. When the magnetic moment and the field are parallel, there's no torque. So if that was the case, you don't have to worry about any equation. There would be no torque. But here there is a torque, and what the torque is going to do is it's going to tend to rotate the loop so that the magnetic moment, which was going into the page, will now point in the same direction as the field. That's what the torque does. And you can figure it out by figuring out what's the direction of the force on each segment, and you'll see that it's going to make it rotate that way, so that this mu now points to the right, and the loop is the way that I just drew it. So now that we know that there's a torque, then it's a matter of plugging things in here. There's only one loop, so n is 1, and so we're going to have mu is I times A. The area of a square is L squared, right? Length times width. And then we have B. And right now, the angle was 90 because mu was perpendicular to B. So that angle was 90. Sine of 90 is 1. So this becomes 1. So the torque becomes I L squared times B, which is choice C.